Chapter 23 centers on distributed database concepts. An introduction. Distributed computing systems in general consist of multiple processing units scattered across something that are interconnected by some form of a network. The degree of distribution depends upon the particular instance. Generally speaking, though, they're fairly close to each other. Nodes cooperate to perform certain tasks, so they're working together to do something in common, and there's typically partitions of large tasks are spread across multiple of these units so that you can solve the problem in a more efficient way. Big data technologies are similar in a way because they do combine distributed and database technologies, but they also deal with vast amounts of data that also may be of varying types and also of varying quality, and typically is moving very quickly. Our first discussion of distributed database concepts. So what constitutes a distributed database? It's a connection of database nodes over a network of some sort, so they're not centrally located on a single computer. There's a logical interrelation of the connected databases, so they have something to do with each other. They're not just standalone and happen to be on the same network. And there's possibly absent of homogeneity among the connected nodes. And what that basically means is those nodes may be differing in what they look like. They may not all be the same exact type of computer. May not even be the same necessarily database management system or distributed database management system. And a distributed database management system is a piece of software that manages distributed databases. A local area network is a means of connecting computers together. It's typically associated with switches and hubs, and there are cables that are involved, typically speaking, that are connecting sites together. Long haul or wide area networks include things like satellite connections, wireless networks, potentially, fiber optics, and various other types of connectivity. Network topology defines the communication path, so how things are hooked together, and transparency is about related to hiding the implementation details from the end user. There are various types of transparency. They include things like data organization, so the location transparency and naming transparency. Basically, this means that you don't necessarily need to know where something is stored in order to use it. Replication transparency is you don't really care how things are kept in sync and how data gets from one place to another. Fragmentation being that data may be split or sharded in various ways, and you don't particularly care if it's vertical or horizontal as long as the queries that you submit return with appropriate values. The design is also something you don't necessarily care too much about, nor do you care about how the things are actually executing. Those things should all work without you necessarily knowing how it's being done, so it's essentially abstracted from consideration. Here's an example of a distributed database diagram. And the primary distinction here is that it's potentially including a geographic location connected together by some form of a network. Availability and reliability is very important within a database, a distributed database, as any type of database. Availability speaks to the probability that the system is continuously available during a certain window. Reliability is that the probability that the system is running and not down at a certain point in time. Both directly relate to faults, errors, and failures. Fault tolerance is an approach where one attempts to mitigate and manage these sort of conditions through either software design or hardware. Horizontal scalability deals with expanding the number of nodes in a distributed system to include or to increase the capacity essentially of the system, whereas vertical scaling is about expanding the capability of a given node or instance inside of that cluster. Partition tolerance deals with the fact that the system should be able to continue operating while the network is potentially partitioned, meaning that there may be some link within the network that is not necessarily available at a given point. When it becomes available, things should return to a good state. So the system shouldn't go down if one partition, one link essentially within the network goes down. Autonomy determine the extent to which an individual node can operate by itself. Design autonomy deals with the independence of data model using and transaction management techniques among the various nodes. Communication autonomy determines the extent to which each node can decide on sharing information with other nodes. Execution is about how much an individual node can, the independence of users to act as they please. So who can do what? Advantages of distributed databases include things like improved ease and flexibility of application development, development at geographically dispersed sites, increased availability, isolate faults to their site of origin, improve performance through the use of data localization. Basically, that just means that the data is where it is going to be used. Easier expansion via scalability. So it's easier to increase the capacity of a distributed database because you're adding additional nodes to the processing and storage capabilities versus having to go and potentially buy larger hardware. Section 23.2 deals with data fragmentation, replication, allocation techniques for distributed database design. Fragments are basically logical units of data that may be sharded or separated out into small pieces. Horizontal fragmentation is called sharding. That's where a horizontal fragment or shard of a replication is a subset of the tuples in a given relation. It can be specified by a condition of or one or more attributes or by some other method. This is deciding how you're distributing those shards. Groups of rows to create sets of tuples. Each subset has a certain logical meaning. Vertical fragmentation is about defining a relation vertically by columns. It's by putting columns in certain locations based upon need. Keeps only certain attributes of the relation. Complete horizontal fragmentation, you essentially are applying a union operation to the fragments to reconstruct at a given location. Complete vertical fragmentation is to apply an outer union or full outer join operation to reconstruct the relation. You typically don't see as much vertical fragmentation as you do horizontal. Sharding is very commonly used. Vertical fragmentation, not quite so much. There are also mixed or hybrid fragmentation approaches. This is a combination of horizontal and vertical fragmentations. A fragmentation schema defines a set of fragments that include all the attributes and tuples in the database. Allocation schema describes the allocation of fragments to nodes of the database management system or the distributed database system. Full replication of distributed databases, that's where replication of the whole database at every site in a distributed system. This improves availability remarkably, but it also updates operations can be very slow because they have to be updated across the entire system. Non-redundant allocation with no replication, or maybe it's some a certain amount of replication. Each fragment is stored at exactly one site, and there are also this concept of partition replication, where some of the fragments are replicated and others are not. This is defined by a replication scheme. And the data allocation, which is data distribution, each fragment assigned to a particular site in the distributed system. Choice depends on the performance and availability goals of the system. There's also this concept of potentially having enough data replicated so that you can reconstruct it if one of those nodes were to fail. So perhaps you have 3 copies of the same data located in various locations, and you keep track of where those are at so that if for some reason 1 or 2 of the systems go down, you still have not lost the data. Examples of fragmentation, allocation, and replication. A company has 3 computer sites, 1 for each department. Expect frequency access by employees working in the department and project controlled by that department. This is in figure 23.2 and 23.3 for examples of fragmentation among the 3 sites. The 23.3 talks about the overview of concurrency controls and recovery in distributed databases. Problems specific to distributed database management systems include multiple copies of data items, failure of individual sites, failure of communication links, distributed commits, and distributed deadlock. So a particular copy of each data item designated as a distinguished copy locks are associated with the distinguished copy, primary site technique. All distinguished copies are kept at the same location. Kind of a little risky because it's kind of all of your eggs in one basket, if you will, so probably not a great idea. Primary site with backup, locking information maintained at both sites. Primary copy method distributes the load of lock coordination among various sites. Voting methods as a way of doing concurrency control. There's no distinguished copy. Lock requests are sent to all sites that contain a copy. Each copy maintains its own lock. If the transaction that requests a lock is granted that lock by a majority of the copies, it holds the lock on all copies. Generally speaking, there's a timeout, and there's always a timeouts of some sort with distributed systems. The results in higher message traffic among sites because you have to do all this voting and communicating back and forth. Distributed recovery. Difficult to determine whether a site is down without exchanging numerous messages with other sites. Distributed commit. When a transaction is updating data at several sites, it cannot commit until certain its effects on every site cannot be lost. Two-phase commit protocol often used to ensure correctness. In the past, that was certainly true of centralized locations. We've now moved to something called eventual consistency, which we'll probably be discussing shortly, but the idea that eventually things come into compliance or into consistency. 23.4 is an overview of transaction management and distributed databases. Sometimes you have a global transaction manager. It supports distributed transactions. The role is temporarily assumed by a site at which the transaction originated. It coordinates execution with the transaction managers at multiple sites, passes database operations and associated information to the concurrency controller. Controller is responsible for acquisition and releasing of all the locks. The commit protocols, there's a two-phase commit. Coordinator maintains information needed for recovery. In addition to local recovery managers, there's a three-phase commit where it divides the second commit phase into two subphases. Prepare to commit phase, and it communicates the results of the voting phase, and then a commit subphase, which is the same as the two-phase commit counterpart. 23.5 is query processing and optimization in distributed databases. The stages of a distributed database query is query mapping, refers to global conceptual schema. Localization maps to the distributed query to separate queries on individual fragments. Global query management strategy selected from the list of candidates. Local query optimization common to all sites in the database, distributed database. Query processing and optimization in distributed databases continued. Data transfer cost of distributed query processing, cost of transferring intermediate and final result files across the network. Optimization criteria is the reducing amount of data transferred. Distributed query processing using semi-join reduces the number of tuples in a relation before transferring it to another site, sending the join columns of one relation R to one site where the other relation S is located, and then join the attributes and result attributes shipped back to the original site. This is an efficient solution with minimal data transfer. Query and update decomposition. Users can specify a query as if the DBMS were centralized. If full distribution, fragmentation and replication transparency are supported. A query decomposition module breaks up a query into subqueries that can be executed at the individual sites. Strategy for combining the results must be generated, and catalog stores attribute list and/or guard conditions to make it all possible. Factors that influence the type of distributed database management system is the degree of homogeneity of the database management systems or the distributed database systems. Your two choices are totally homogeneous, and then there's heterogeneous where they're made up of different sorts of things. The degree of local autonomy, there's either no local autonomy or multiple databases. Multi-database system has full local autonomy. Federated database systems, global view or schema of a federated data of databases is shared by the application. classification of the various types of databases shows that it's 3 dimensions: distribution, autonomy, and heterogeneity across and putting things into that 3-dimensional space. The types of distributed database systems: there's federated database management systems that they have the following issues. There's differences in data models, there's differences in constraints, and there's differences in query languages. Semantic heterogeneity is there's differences in meanings, interpretation, and intended uses of the same or related data. Design autonomy allows different definition of the following parameters: the universe of discourse from which the data is drawn, representation and naming, understanding, meaning, and subjectivity, subjective interpretation of data, transaction and policy constraints, and then derivations of summaries. Communication autonomy is to decide whether to communicate with another component, distributed system, database system. Execution autonomy: execute local operations without interference from external operations by other components of the system. Ability to decide on the order of execution. Association autonomy: decide whether and how much to share its functions and resources. 23.7 talks about distributed database architectures. There's parallel versus distributed architecture. The types are also of multi-processor system architectures. So a parallel architecture would basically be things happening together, but typically speaking on the same computer. Distributed, you're running on different computers, different processors at exactly the same time. A distributed system is inherently parallel in nature, but a parallel system need not necessarily be distributed. Types of multiprocessor system architectures: there's shared memory, which is tightly coupled. A shared disk, a little less tightly coupled, but using a disk still that is common to everything to communicate, or a disk-like system. And then shared nothing, where there's no coordination between them at all. Database system architectures: the figure A is showing a shared nothing architecture. That has become very common. Figure B is a network architecture with a centralized database at one of the sites, and a fully distributed database architecture is figure C. Generally speaking, things are going to be a shared nothing, or possibly a truly distributed system, which you see in C, or a variation where it looks like it's a shared system. So it looks like it looks like B, but it's not really B, because it's logically distributed, or physically distributed, but logically appears to be not distributed. The general architecture of a pure distributed database system includes things like a global query compiler. It references global conceptual schema from the global system catalog to verify and impose definition constraints or define constraints. A global query optimizer generates optimized local queries from global queries. And then you have a global transaction manager, which coordinates the execution across multiple sites with the local transaction managers. Figure 23.8 is a schema architecture of a distributed database. You can see here the users with their external view, the global conceptual schema, the local conceptual schemas depending upon where they're at, and the local internal schema, and then the stored data at site 1 through N. A federated database schema architecture is in figure 23.9. It shows an external schema with some federated schemas, and then an export schema, and a component schema, and a local schema for each of the component databases. An overview of a 3-tier client-server architecture. This is a common architecture, not necessarily related exclusively to databases, but the idea here is a division of a distributed database management system. Functionality among 3 tiers can vary. So you have a client, which is interacting with an application server of some sort, typically over some sort of HTTP or HTTPS protocol. And then you have the application server connecting to a database server, typically using ODBC, JDBC, or some other variant of that sort of connectivity. There's an extension to this where basically the application server becomes a web service instead, and you interact from the client, which may be a browser directly using JavaScript to access a web API to perform interactions that is then backed by a database. So a very similar architecture. 23.8 is around distributed catalog management. Sometimes you have centralized catalogs. That's where the entire catalog is stored at a single site. This is the easiest to implement. You have fully replicated catalogs. That's where identical copies of the complete catalog are present at each site. It's faster reads, but you're trading off keeping those things in sync and keeping multiple copies of the same thing. And then you have partially replicated catalogs where each site maintains a complete catalog uh, and information on what is locally stored at that site. In the summary of 23.9, section 23.9, we talked about distributed database concepts. We talked about the concepts of transparency, design issues with horizontal and vertical fragmentation, concurrency control and recovery techniques, query processing, and categorization of distributed database management systems along the 3 dimensions.